Hey, more graphing. This is the 7 through 12 from this function review. And sorry, I have the wrong date on there. We have to update that. It is actually 2020, 2021. It's hard to keep track of time these days. I don't know if you're having that experience, but we're not living in the past. Not yet. All right, so 7 and 8, it says to do on the same set of axes. So 7 and 8, I'm going to throw down right here. So log base 2 of x. Okay, so let's see. Remember how to do that. How do you graph log base 2 of x? What does that mean? Okay, so logarithms, when I plug something in here, what I'm asking, the logarithm says, what do you have to raise the number 2 to? What exponent do you have to throw onto a 2 to get this number? So some of the easy things to plug in here, if I was going to make a little table, if I put 0 here, right here, what do you have to raise 2 to get 0? Well, you actually can't do that. There's no exponent you can raise 2 to the power of something and get 0. It's not possible. What about 1? What do you raise 2? What power do you raise 2 to? So you're kind of thinking this. If I put a 1 here, what do you raise 2 to? Well, 2 to the 0 power. Anything to the 0 power is 1, right? What if I put a 2 here? Put a 2 here. What do you have to raise 2 to get 2? Oh, the first power. What if you put 3 here? Oh, I don't know. I mean, what do you raise 2 to get 3? There's some like messy decimal number, but that doesn't seem like a good idea to try to figure that out without a calculator. So how about 4? What do you raise 2 to get 4? You raise 2 to the second power. And then the next nice number is going to be 8, right? So 2 to the third power. If I put an 8 here where the x is, then I have to raise, this is like our y value. Alright, so that's kind of what's going on with a logarithm. So I got the point 1, 0. I've got the point 2, 1, 4, 2, and 1, 2, 3, 4, 5, 6, 7. So 8 would be like right about there. And then what happens, I can't plug in 0. That's actually an asymptote there. And if you did plug in, uh-oh.
If you have additional items that need to get to students, please bring them to the main office. Do not take them to the gym. There are no books in the gym any longer. Please do not take items to the gym. Just bring them to the main office. Thank you.
There you go. You guys got your stuff already from me, I think. So 1/2, if I put a 1/2 here, then 2, remember you can, that negative exponents flip things over. So 2 to the negative 1 power is 1/2. And so if I plug in 1/2, I get negative 1. And then this thing just plunges down like this and never crosses that axis. And that's what a logarithmic graph, a logarithmic curve looks like. All right, so let's see if we can answer some of these questions now. I got 5 points. If the function has an inverse, how do you invert something like this? Well, if I have y equals log base 2, actually let's switch them. So x equals log base 2 of y. Remember that this is the same as saying 2 to the this power equals that. So 2 to the x. So that's my inverse right there. The inverse of a log function is an exponential function, and vice versa. So what does it look like? Well, if I swap all the points here, that goes to there, this goes to here, this 4, 2 goes to 2, 4, and 3, 8. And all these points that are hugging this axis here now hug over here. Right? And that's exponential curves are very useful in modeling all sorts of things, like money growing in a bank with compound interest, or population growth, or how many people in the world have the coronavirus when you're not doing anything to stop it, stuff like that. So there's the inverse of it. And that has, to answer the asymptote question, this, our original one, has a vertical asymptote at x equals 0, and so the inverse has a horizontal asymptote at y equals 0. Even, odd, or neither. These are not even or odd. And we graph the asymptotes, so I think we're good. Except that we're also supposed to do number 8, which is log base 2 of 4x. All right, so let's see, where should we do that? Maybe I'll just go back to this, make a little table here. So here's my x's and my y's. If I plug in 0, yeah, you can't do that. And if I plug in 1, well, wait a minute here. If I plug in 1/4, I'm plugging in 1/4 because 4 times 1/4 is 1, then that would give me 0 here. And if I plug in, let's see, if I plugged in a half, then that would be a 2 in there, and then the exponent would be 1 to get that. And then if I plugged in 1, then that would be a 4 in there, and I'd have to raise 2 to the second power to get that. So it looks like it's getting kind of squashed down here. And then if I plugged in 2, then I get an 8 in here, and have to raise 2 to the third power to get 8. And then if I plugged in a 4, then that would be a 16. That's 2 to the fourth power. So let's see what that looks like. Let me just really quick grab, we'll be right back. Whoa, maybe this pen's blue. Let's see if I got lucky here. No, not really. I just want to grab a pen of a different color. Alright, this is going to be messy, but I'm going to use this blue dry erase marker. So let's see, my little table here. Let's graph these. So I got the same asymptote there, but now I've got the point 1/4, comma 0. So that's like there. And then 1/2, I'm a 1. And then 1, comma 2, which is a point on, that was on the inverse of that. And then 2, 3. And then 4, 4. So I think I'm seeing the shape of it now. It's going to have that same asymptote and look like this. All right, so it's almost like it just got shifted up there. That's interesting. How about the inverse of it? Well, when I swap the x and the y here, I get x equals log base 2 of 4y. So that means 2 to the x equals 4y, and y equals 2 to the x over 4, but 4 is 2 squared, and if you remember, like, I don't know, Algebra 1, I guess you learned this. If you have something to this power over the same thing to that power, that's the same as you subtract the exponents. Y equals 2 to the x minus 2. And that, if we see it in that way, maybe that helps us understand what's going on here. So this, if you have this x minus 2 here, that's like shifting a function over 2 units to the right. So everything that I have here, this is just a quick sketch. It's this curve bumped over 2 units. So something like that is the inverse. And then just a final word about that, like what's really going on here? Well, if you remember your logarithm rules, I know that was a lot to ask of you, But here, if we look at this, f of x is equal to log base 2 of 4x. When you have a product in here, you're allowed to, using logarithm rules, split this up. Split the product up into a sum. So that turns into that. If you want, it's kind of interesting for us to see it here because this is just equal to 2. So that original function here shifted up 2. That's what we got when we did this 4x here. So that kind of explains now why we were seeing what we were seeing with those two graphs. Did I answer all the questions? The even, odd, neither, all of that stuff's neither. We did the inverses, and we did the asymptotes. So I think we're good. All right. 9. We got here the natural log function. So I'm not going to talk about this one too much. It's the same deal as this. It's got the same when you plug in 1. We're going to make our table here of x's and y's. When you plug in 0, you can't. When you plug in 1, then 0. So here, what is natural log anyway? It's like this thing here. It's like this game, except the base of the natural logarithm is the number e, which is like 2.7 and change. So the thing that we're thinking about is this. So when I plug in a 1 here for x, it's like, well, what do you have to raise e to get 1? 0. Whatever e is, that still has to be 0. So what's the next like nice thing I can plug in here? Well, I mean, you could do it with a calculator, but if you just wanted to know a couple points by hand, I guess I could plug the number e in, right? What do you have, if there's an e here, what do you have to raise e to get e? Well, the first power. And then the next nice number would be e squared, whatever that is. It's like 8. So 8-ish. So if I have e squared over here, what do you have to raise e to get e squared? Well, 2, right? Okay, so let's just use those points. So if I plug in e, which is like 2.7, then I get 1. And if I plug in e squared, which is, I don't know, about 8, then I get 2. So it has that same logarithmic shape. But it's a little squished down from the log base 2 because e is a little bit bigger. So if that is bigger, that means the exponents have to be a little bit smaller to get those x values that you plug in. What's the inverse of that? The inverse of that is the exponential function, y equals e to the x, just like what we did there. And that is called the exponential function, just like 1 over x is called the inverse function. It's not by accident that it is called that. So that's sketched in there. And I don't know if you ever think about the names of things, if you ever wondered to yourself when you were learning about logarithms, and then there's this thing called the natural log, and the base of the natural log is like 2.71828 blah blah blah, and you're like, what the heck's so natural about that? Seems like 2 is a little, or 10 or something would be more natural. But there's a really, really good reason, actually reasons, for this being called the natural logarithm. And the best way to understand that is through calculus. And you don't know that yet. So we'll come back to that idea and talk more. I think it'll be probably in chapter 4 that we'll be able to really understand what's so dang natural about this natural log anyway. So we'll put that thought on hold for now. So there's asymptotes here, same as the asymptotes in this one. No maximums or minimums. What else do we have to do? We got some points on there. We were a little short on points here because, you know, not really nice things you can plug in, so that's all right. And I think we're good. Oh, even, odd, neither? Neither. No symmetry. Okay, so number 10. 2 to the x. We did that already, and we did e to the x. So 10 and 11, I'm going to blow through these pretty quick. So 2 to the x is graphed on here because it's the inverse of the natural log of, log base 2 of x. So what does 2 to the x look like? If you plug in 0, you get 1. If you plug in 1, you get 2. If you plug in 2, you get 4. And if you plug in 3, you get 8, because we're raising 2 to all those powers. 2 to the negative 1 is a half, then a quarter, then an eighth. So there it is. That is this is not the exponential curve, but it's a exponential curve. And the inverse of that is, well, that's the log base 2, right? So there's those. I think all the other questions are already answered, right? And then I pulled the same thing on you here. We already did these. So you're going to get the same graphs here, except we're going to start with the exponential curve. If you're wondering, like, how is he plotting those points so fast? I'm just thinking to myself, okay, e to the 0 is 1, e to the first power is e, which is 2.7, e to the second power is about 8, and then e to the negative 1 would be 1 over e, which is, I don't know, about a third-ish, so something like that. And then same thing, when we invert it, we just get the natural log function. And all the same answers here. Now those look real similar, don't they? The difference is the base here is 2 and the base here is e. So if you look closely, they're not quite the same. This goes up a little more steeply and this flattens out a little more quickly because e is a little bigger than 2. All right, home stretch. Number 12. This is 12 and 13 are pretty similar here. I'm going to make a little table, and then we'll talk about what it is we're looking at here. Let's see. So the first thing I might notice here is I'm not going to get too far if I start doing this 0, 1, 2, and so on and so on. When I plug in 0, I get 1. When I plug in 1, I get 0. When I plug in 2, I get the square root of negative 3, which is well, I guess that's I square root 3, but this is not, we don't have anywhere to graph things with i's in them here. This is like the x-axis and the y-axis. These are all real numbers. So this is Garbaggio, or I should say, like, that's undefined. If we're just working with real numbers, cannot do that. And in fact, anything bigger than 1, I think we can't, oops, sorry, you can't see that. There we are. Anything bigger than 1, we can't do that. So it wouldn't make sense for me to make this 1 on my graph. I think I'll do, let's see, 1, 2, 3, 4. Maybe I'll make this one like that. And I'll do the same thing. So I'll give me a little bit more room. So it looks like I got, if I plug in 1, if I plug in 0, I get 1. If I plug in 1, I get 0. If I plug in negative 1, I also get 0, and you can't go past negative 1 for the same reason we just talked about. So what other things could you plug in? This graph only exists in between here and here. Let's see, what if I plugged in a half? Then I get, let's see, a half squared is, a fourth. 1 minus a fourth is 3/4, and the square root of 3/4 is the square root of 3 over the square root of 4, which is 2. So that's 1/2 comma square root of 3 over 2. 1/2 comma square root of 3 over 2. That's somewhere around there. And then if I plug in negative 1/2, the same thing happens because I'm getting squared. So noting that, excuse me, since I plug in positive or negative number, it doesn't matter. That means I'm going to have an even function. Now, I guess if I plugged in the square root of 3 over 2, then when I square that, I'd get 3/4, and 1 minus 3/4 is a quarter, and the square root, it just kind of does the backwards inverse of what that happened there. So that would give me a point like something like here. And well, that's you know what this is? This is the top half of the unit circle. And that didn't come out of nowhere. If you look here, if you took this and squared both sides of it, y squared equals 1 minus x squared, and then you move the x squared to the other side, you get x squared plus y squared equals 1. That's the equation for a circle with a center at the origin and a radius of 1. That's the unit circle. How come I didn't get the bottom half? Well, y equals this thing, that's going to give us a function. If you threw a plus or minus in front of this, then you'd also get the bottom half. So this is going to come up here and there for us later in the year. It's not the worst thing in the world if you see something like this and you recognize, oh, that's the top half of a circle. So let's see. We got some points on there. What else do we have to do? Can we invert it? No. If you inverted this, you'd get this side piece. But you could restrict the domain of this to just the positive x values, and then you'd get, you'd just get the first quadrant version of that, and the equation would be the same thing because, well, I'll let you try that if you want and see what happens when you swap the x and the y and try to solve for your new y. You get the same thing. So you'd have to, if you want to invert this, you'd have to restrict the domain to just this piece of it, and then you'd get its own self. It is even. And what else do we need to do? Any asymptotes? Nope. Any maximums or minimums? Yep. That's a maximum. And these are actually minimums, too, if we're just looking at the top half, because there's nothing else lower than those points, even though they're dead ends. And I think that's all we need to do with that one. How about 13? We have similar. It's there's a 2 in front of it now. So let me do a little bit of work on this sheet where I have a little more room. So what's going to happen in my little XY table? I'm just going to borrow from what I did here. All these y values are just going to get multiplied by 2, right? Because I got a 2 out front there. So I'm not going to redo all that. Like 0 and then double that. Plug in 1 and then you double this. And then all the stuff that's outside of 1 and -1, can't do that. If I plug in 1/2, then double this. If I plug in the square root of 3 over 2, then you double this and you get 1. And then all the negatives of these give the same things. Alright, so let's see what that looks like. So 0, let's see how I'm going to scale this. I guess I'll do the same scaling. I'll do 1, 2, 3. I'll make this 1, and then 2 would be here. This would be 1, and 2 is just a little off the graph there, but I think we can handle that. Alright, so 0, 2. I get a point there, and then 1, 0. Okay, so it's not a circle because that's not symmetric enough. When I plug in 1/2, I get the square root of 3, which is like 1.7, I think, ish. So that's like up here somewhere. And then when I plug in -1/2, the same thing would happen. When I plug in -1, same thing happens. And if I plug in the square root of 3 over 2, which is like 0.86 or something, pretty close to this, getting up there, I get 1. So it looks like, I guess that's not really surprising when we realized we were just doubling all the y values. So it's like taking this and like stretching it up by a factor of 2. Now, we think about this. If we wanted to understand what's happening here, what if we squared both? Let's write a y here instead of that. If I square both sides, if I square this, that turns into a 4, and this turns into 1 minus x squared. Let's see, so that's y squared is equal to 4 minus 4x squared, and then I move that over, 4x squared plus y squared equals 4. And I don't know if you remember your conic section stuff. I don't even know how much we still teach about conic sections. If I divide everything through by 4, this is the equation for an ellipse in standard form. So instead of getting the top half of a circle, I've got the top half of an ellipse. And this is an ellipse that is centered at the origin, if you remember how to recognize that. And this is like the b squared. That tells you how much it's stretched in the y direction. One way of thinking about an ellipse is kind of like a circle, except it's got like one radius in this direction and then a different radius in the other direction. So the number under here, if you want to see one, would be like a 1. So the x radius is the square root of this, and the y radius is the square root of this. 2 up and 2 down if we had the whole thing. For the same reasons in number 12, I'm only getting the top half of it. If you wanted to invert this, you would have to restrict the domain of the original to just positive x values, because otherwise you wouldn't pass the horizontal line test. It's going to look like, if you invert it, it'll look like you just turned it on its side. Like that. I'll let you do the algebra there if you want to swap the x and y and figure out what the new one looks like. Remember that inverses are reflections over that line. I can see that reflection. If you did the whole thing, it's almost like making a little heart shape. Oh, I love ellipses and conic sections. If the conic section stuff stresses you out and you're like, oh my god, I don't remember that conic section stuff, this is really stressing me out. We really aren't going to do a lot with conic sections, at least not in the way that you might have studied them in pre-calc or algebra 2. So we're certainly going to look at, parabolas, and circles will be important because the unit circle and stuff, but not really like heavy conic sections. So I threw these in here because I think it's important for us to recognize this, that's the top half of the unit circle. And that is all I got for you about these graphs. Have a great day.